Chapter 6, Section 3, Part C. Enzyme Kinetics as Approach to Understanding Mechanisms. Now, up till now, Section A, starting off in A and really heavily in Lecture A for this section, and really in Part B for this section, we talked about rates. Rates as a means of trying to understand the mechanisms that allow enzymes to take substrate, turn it into product. Okay? As I talked about in the intro lecture for this chapter, we have to have a way of controlling this, though. We can't have enzymes just working all the time. And we can't use transcription translation, as our mechanism for control. It takes too long to go from, the manufacture of mRNA to having a final translated polypeptide that's correctly folded and ready to work. So we have to have control mechanisms, ways of turning on, turning off. We see that many enzymes are going to have some form of inhibitor, a molecule or something that interferes with catalysis, either slowing or halting it completely. All of these inhibitors are going to fall into two classes. Either they're reversible or they irreversibly turn the enzyme off and then there's no coming back from it. Reversible inhibition is the one that we like to focus on most. Are we competing for the active site? Because remember, for substrate has to get into the active site for E plus S to become ES. Well, what if there is another organic molecule that can enter in because it's got kind of the same shape, but it doesn't have the complete shape, so you're not going to have the R groups interacting, thus you're not going to have an ES formation, that transition state. That can be a competitor. It's competing for the active site with the true substrate. Because if that competitor is in there, the substrate, the true substrate, can't get in. Uncompetitive inhibition, well, it means you're going to have something that's going to bind somewhere else on the enzyme and disturb its shape. Active site no longer has the correct shape. Substrate can't get in and interact. Or no, even if it gets in, there's no interaction. So you have A, you have B, and then you have a kind of all of the above. So as I said, if you have an inhibitor, the inhibitor, as you see here, is going to enter into the active site. It does not have the complete shape. It does not have the complete molecule or macromolecule or whatever S is, so it can't be changed. You can't have the ES formed, thus you can't have the E plus P. But for that instant that the inhibitor is in there, you shunt this way. You shunt back, shunt this way, shunt back, as long as that inhibitor is there. The inhibitor gets kicked out because it's not associating. Well, now you have a competition. Who's going to get back in first? I or S? I or S? This is a type of reversible. Because at no point in time is the enzyme perturbed. What's happening here? Your level of inhibition, high level, low level, is directly proportional to how much inhibitor. Very low amounts of inhibitor, high levels of product, minimal levels of interference. But as the inhibitor goes up, the final product level decreases. You get more and more inhibition because you have more of the I than you have the S present. More often than not, I is getting into the active site, not S. So we have to take this into account if an inhibitor is there, a competitive inhibitor. We go back to our Michaelis-Menten equation. V naught equals Vmax times S, Km plus S. Remember our original? Well, we now have to take into account there. A, the alpha, is 1 plus the concentration of inhibitor divided by Ki. K and I, K inhibitor, is total concentration of E, total I, divided by the EI. Remember, this is going to be fleeting. This isn't a true ES like we've seen before. Vmax will always stay same, even if you add in a competitive inhibitor. What's going to change, though, is that our curve will begin to shallow out as you increase the inhibitor concentration, so that our Km keeps going up and up and up. So you have to keep increasing the level of S, the substrate, to counter how much inhibitor is present. So if you have the concentration of S that is so much greater than I, remember I told you have low I, you're still going to have maximum amount of product, which means your Vmax is not going to change. You keep raising your I, as I says, alpha 1, 2, 4, product goes down. You're going to have to increase the substrates to counter that increased inhibitor concentration. As you see here, Km1 for, alpha 1. Alpha 4, boom, you've gone from 10 to 40. Your concentration has increased dramatically, just so that you have the same reaction rate. Okay. No inhibitor, more inhibitor. So as you increase I, our 1 over Vmax, remember Vmax stays the same. What changes, though, is right here. Our alpha Km starts to approach 0 as you increase inhibitor. So our 1 over V naught equals alpha Km divided by Vmax plus 1 over the concentration S plus 1 over Vmax. Our Y equals Mx plus B. Inhibitor increases, our slope, which is different when we're just plotting V naught over concentration of S. You saw the hyperbolas got shallower and shallower. Uncompetitive means that there's going to be a spot somewhere else for an inhibitor to bind, not the active site. If I binds, it disturbs the shape of. Does not allow for S to bind, or does not allow for the ES to EP to finalize. So the ES is held in place in this uncompetitive. Can't get that final reaction to occur where you go from ES to EP to free enzyme plus product. It's held right there. This is reversible because, well, I could be plugged off. As soon as I is removed, ES becomes E plus P, free enzyme plus product. Okay, well, what's this look like? Well, instead of V naught Vmax over S divided by alpha Km plus S, well, here with uncompetitive, the alpha, now here alpha prime because it's an uncompetitive inhibitor, is now going to be multiplied times the S, the concentration of S. Alpha prime, ES, instead of the E times the S that we saw before with competitive, now it's ES times I divided by the ESI. Here, though, if you have the uncompetitive inhibition, if the I binds at the same time you have the enzyme substrate transitional state, this actually does lower Vmax. Competitive inhibition, remember, doesn't lower Vmax. Here it does. So the Kms are actually going to be quite close to each other. Yes, there will be differences because as Vmax lowers, our half rate will lower, and we become more of a shallower hyperbola. But it's not the 10 to 40 change we saw with competitive. Here, when you go and you graph them out, Vmax, I'm sorry, the 1 over Vmax with the point here on the Y, no. You now have what is referred to as alpha prime over Vmax, and this changes. It increases as you increase the concentration of inhibitor. K alpha prime over Km, so it's not 1 over Km here, it's now alpha prime over Km. That also decreases. They stay perfectly parallel. Whereas competitive, remember, it all had the same point on the y-axis, and it just moved that way. Now, if you have mixed inhibition, both competitive as well as the uncompetitive. So this is kind of in-between thing. Still reversible. We haven't changed the shape of the enzyme, so we're not changing, interfering with its ability to function. Here now we take into account alpha as well as alpha prime. Vmax will be lowered. Km greatly increases as you increase the level of your inhibitors. And here, what we see is that the point where they overlap, okay, they're not parallel here because you're taking a mix of the both. But now that intersection where all these slopes of the lines intersect is not at the y-axis, it's far off. Alpha prime divided by alpha Km, we see it starts to approach 0 as you increase our inhibitor. And our alpha prime over Vmax, instead of the 1 over Vmax, our alpha prime over Vmax also increases as you increase inhibitor. Okay, but let's look at non-competitive. Here, this is going to be a special case. Alpha and alpha prime are the same. If you have, using reversible, Vmax, Km when there's none inhibitor, these are normal. Competitive, Vmax stays the same, Km roughly the same. Uncompetitive, Vmax divided by alpha prime, but remember when you're graphing it, you're flipping, you're taking the reciprocal, hence the alpha prime over Vmax. Mixed, alpha prime, alpha Km, alpha prime. Irreversible inhibition means you're actually going to change something about the enzyme. You're going to have something bind covalently or destroy a functional group within the active site. Here what you see is you have serine 195 has a methyl hydroxyl here, CH2 hydroxyl. you're going to come in with DIFP. I forget what this actually is. But you see it has a fluorine right there. Phosphate group with a fluorine right there. The fluorine is going to be released, and now you have a phosphate group that's going to interact, because this hydrogen here on this hydroxyl is also getting kicked out with the fluorine. And now you have an enzyme, and it's serine 195 has irreversibly now had DIF or DIP covalently bonded to it. This now will not interact with any substrate. This may actually make the active site more acidic, or it may make it so that the substrate, can't position correctly to interact with other R groups. They think of these as a suicide inactivator. Okay, you're inactivating this enzyme by adding something to it irreversibly, so it is now completely shut off. This enzyme now has to be ubiquinated and recycled. It's not going to have any function. You can't go in and remove all of this from serine 195. You also have what are referred to as transition state analogs. These are molecules that can get in, and they're going to allow the first few steps to occur in the going from E plus S to an ES. So you're going to see fructose 1,6-bisphosphate. We think it has this transition state here. But if you take an analog of this, something that closely resembles this, anything that's this is now going to get into the active site of, what is it? Glyceraldehyde 3 phosphatase, I believe. Oh, no, wait. I forget which one that is. Goes through, and it's not going to allow this to continue on and have all of these electrons, as we're seeing here, moving around, so you end up with dihydroxyacetone phosphate. You go through, the enzyme is going to cut, it's going to change this over here. Hydrogen is going to be carried off here, or a nucleophile, an electron here. The electron, this oxygen, boom. So this now becomes this carbonyl. That hydrogen is going to be released. Or I'm sorry, it switches over to here. Okay, yeah. Electron here, boom, boom. This hydrogen fills in for that covalent bond, HC. This one's now going to swap over here, so you get this carbon-carbon double bond. This covalent bond here is going to swap up, and the zinc going to remain. The zinc will be released at a different point because this zinc, the zinc finger, is part of the enzyme that's cutting this in half, and I'm sorry, I can't remember it. I should remember my glycolysis steps. But this transition state analog looks and approximates this, but not enough to allow for the finality of. It binds in. In this, analog is going to bind into the active site that should be allowing these different electron shifting, these bond shifts to occur, thus interfering with the